Hello, everyone. Happy New Year, and welcome to this calendar year and this quarter's first Zoom for Thought talk, during which Nick will tell us how hard it is to be a salesman. Take it away.
I think that's exactly what's going to happen. So yeah, thank you, Vaki and Sam and Mr. Thought. I was hoping I could give this talk in person, but such is life right now. This will suffice for today. So today I'm going to tell you about one of my favorite things in theoretical computer science, the traveling salesman problem. And sort of the goal of the talk is to convince you all that this is a reasonable thing to care about or be interested in and study. So sort of more explicitly, the goals are going to be to introduce the classes P and NP and sort of say what that means. We're going to talk about NP completeness and why we should care about NP complete problems. We'll talk about how to show a problem is NP complete, and then we'll finish by showing through a pretty good series of proofs that the traveling salesman problem is indeed NP complete. First, I do want to mention before we sort of get into things that there's generally two approaches when it comes to this kind of stuff, the theoretical CS stuff. The first is to take the really formal mathematical sort of model of computation approach, where you talk about determinism and non-determinism and give a formal definition of a Turing machine and talk about Turing decidable languages and all that kind of stuff. That's all well and good. It's a bit detail heavy for the time we have today. So I'm going to take you can call it the more computer sciencey approach, where it's just like you say like, here's an algorithm and do everything in terms of sort of an intuitive notion of what an algorithm or a program is. So rest assured, the pure mathematicians among you, that like everything I'm doing can be formalized very concretely, but I'm going to be a bit hand wavy about some of the technical details about the things we're defining. All that said, there's still a number of definitions that we need to sort of get out of the way, just so that we're all on the same page in terms of some of the language. So the first thing I wanted to define is what a decision problem is. And it's just a question that has a yes or no answer for each input. And you're all probably used to thinking about the traveling salesman problem as some kind of optimization question, where you have a graph and you have like a weighted graph, and the question is there a path that hits all of the nodes? Or I guess the optimization problem is what is the smallest weight path that hits all of the nodes, right? It's not a decision problem though. So the decision problem version of this is going to be something along the lines of, given some graph and some number, is there a path whose weight, or who hits all the nodes and whose weight is at most that whatever number that was? And now that does have a yes or no answer. And so it is a decision problem. And the reason we care about decision problems is Turing machines are things that, again, they're procedures or algorithms, whatever technically that means, sort of whatever you think of as a program, that takes in an input and does one of three things. It's either going to output yes, output no, or it's going to loop forever. And if it outputs yes, we say it accepts the input. And if it outputs no, we say it rejects the input. And this is why we care about decision problems, because these Turing machines formally only ever output yes or no. They can't necessarily give you like, here is the best. It just says, it says yes or no. And we say a decision problem is Turing decidable if there is some Turing machine that outputs the correct response for each input. Sort of, again, intuitively, if you can write a program that is going to decide this thing in some finite time. Any questions about any of the three definitions we've given here before we move on to yet more definitions? Okay, cool. So plowing ahead with more definitions. We say a Turing machine, or consider a Turing machine that halts on all inputs. So something that is always going to stop. We say that program runs in time f if the number of steps needed to perform the computation on an input of size n is at most f of n. If you've ever taken an algorithms, like analysis of algorithms class or numerical analysis, or done anything with any sort of runtimes, this is exactly what the intuition is. This is just the runtime of the algorithm, usually denoted with some sort of big O notation. So given that, we can finally define what P and NP are. So we say a decidable problem, something that has a program to decide it, is polynomial time decidable if there's a program that decides it in, namely, polynomial time. These are sort of not necessarily creative names. So, good example of a thing that's decidable in polynomial time, something like, I don't know, is this number prime, right? You can sort of just iterate all of the numbers smaller than it and divide them in constant time and check if any of them are factors. And if they are, you output no. And if none of them are factors, you output yes. And you can do this in linear time. So this would be an example of some kind of polynomial time algorithm for solving something like that. And the class of such problems is the thing that we call P. On the other hand, NP is the class of problems that are what we call polynomial time verifiable. And verifiable here just means that there's some certificate if the input is accepted by the Turing machine, we want some certificate that we can sort of pass to a new Turing machine as evidence of membership. So explicitly in the traveling salesman example, this is the traveling salesman problem, the decision problem version is in NP. And the reason it's in NP is that maybe I don't know if such a path exists that is of weight smaller than W, but if there is one and I hand it to you and say, this is I claim here's a graph, it does have a path that hits all the nodes and has weight smaller than something, and I hand you that path and said, here is the order of the path, you can then sort of in linear time check that, okay, yes, you step through all the nodes, I hit all the nodes, and the total weight was indeed smaller than the thing you claimed it was smaller than. So as we will see, it's very hard to find such a path on your own, but if you are presented with one, you can check that it is a valid path in polynomial time. In the traveling salesman problem, it's sort of linear in the number of nodes. Any questions on what it means to be NP? I know if you haven't seen this before, it may be a little bit strange thinking about certificates and things, but is this sort of the difference between verifiability and decidability? Is that sufficiently clear?
I assume NP means not P, and so P and NP are disjoint and therefore not equal, right?
Okay. Yeah, I should have mentioned this. I didn't. We'll talk about the P versus NP problem in a second. NP does not mean not P. It means non-deterministic polynomial. Again, whatever that means, I don't really want to get into the details of determinism and non-determinism. You can sort of think of non-determinism as this checking all of the possible certificates in parallel is more or less what that boils down to. Again, if you're sort of interested in all the details of what non-determinism formally means, please do ask me afterwards. I'd love to talk about it, but it's going to take us a bit of.
I've got a quick question.
Yeah, go for it.
What is a certificate?
Yeah, it's some kind of object. Again, formally, all of this is going to be done in terms of strings. If you really define a Turing machine, it's going to input a string and output a binary thing. The conversion from how do you take a graph and turn it into a string, that's going to be a bit sort of fuzzy, and you can do it formally, but not necessarily something I want to spend a ton of time discussing. So what you should be thinking about is it's some kind of object that you could pass to a pass to a computer program. If you know what linked lists are, then the traveling salesman problem, you can pass it a linked list as the certificate and just sort of like the list of all the nodes, and there you go. But maybe sort of more mathematically precise. We may want to save that for later. Is that fair? Does that answer the question? Okay, cool. Anything else?
Yeah, I have a question.
Yep.
So does decidability depend on a Turing machine, or is it independent of a Turing machine?
Decidability means, I could go back. Decidability means that there is some Turing machine that decides the problem. It's a property inherent to the problem. And if there is any Turing machine, if there's any program that decides it, namely it spits out the whatever you just want to define as the correct output for each input, then we say the problem is decidable. So it's decidable basically means I can write a program that does the thing I want it to do.
Thanks.
Okay. All right. So slightly more definitions, but we're getting to now we sort of get to the exciting stuff. We say something is polynomial time reducible. So two problems. We say one is polynomial time reducible to the other if there is some function that takes inputs in A and outputs inputs into B, that such that we can compute f in polynomial time, sort of in the way we just described, and that A accepts W if and only if B accepts f of W. And again, I know this is slightly sort of hand wavy for a lot of you, but there's precise definitions for here. But again, intuitively, we want some polynomial time procedure for taking an input in A, spitting out an input in B, such that A and B sort of have or that those outputs have the same membership in A and B. And it might help to give an example here. So consider A the problem of, is this natural number divisible by 4? Not a super hard problem, but a decision problem nonetheless. And B is the problem, does this string end with 2 zeros? And the claim that maybe isn't all that hard to convince yourself of is that I can reduce A to B in polynomial time. Explicitly, I just take the reduction is going to be take the integer k and write out its binomial or its binary expansion, and then check the last two numbers. Are they both 0? If the answer is yes, then the original number was divisible by 4. And if they're not, then it was not divisible by 4. And so this is also important to note. You can do this in polynomial time. In particular, I could do this. You can probably do this in something like log time, but at very worst, it's polynomial. And so in this sense, we say that like B is a harder problem to solve than A, or at the very least, isn't easier than A. Because what this shows is that if I have a solution to B, then I can produce a solution to A very easily just by pushing stuff to B and then solving B. Right? So we sort of intuitively, we think of reducing problems to easier ones. But when we do that, we've actually said computationally, the thing I've reduced to can't be any easier, because the thing I reduced to it is now solvable if the new thing is solvable. So if I can solve B, I can solve A very quickly, just by this polynomial reduction to B. Cool. Questions about reducibility? All right. So then now we get to the really good stuff, NP completeness. We say a decidable problem B is NP complete if, and first and foremost, it's in NP itself. So it has to be polynomial time verifiable. And also, for any other problem that is polynomial time verifiable, there is a polynomial time reduction from that problem to the thing I claim is NP complete. That's what it means to be NP complete, that it is an NP, and in sort of the sense we were talking about a minute ago, that it's somehow like at least as hard as every other problem in NP. Because if I can solve B or if I can solve B, then I can solve A then I can solve anything just sort of by the reduction given by NP completeness. And the reason we care about NP complete problems is this sort of theorem that like feels interesting and really is just immediate from the definitions, that says that if B is NP complete, then it's NP if and only if P equals NP. Because again, if I have a reduction from any NP problem to B and I can solve B in polynomial time, then I polynomial time reduce to B and then polynomial time solve B. Composition of polynomials is polynomial. That gives a polynomial solution for A. And A was an arbitrary NP problem. So this shows that P is indeed NP. So in some sense, these are the only NP complete problems are kind of the only problems anybody cares about in talking about the P versus NP problem, because if you can show any of them are NP, then triumph, right? P equals NP. If not, if P doesn't equal NP, and most people think it doesn't, these are like sort of the first candidates you want to look at, because in some sense they are the hardest NP problems. So if there are any candidates of things that are going to be an NP but not in P, NP complete problems are those. There's no, if P is not NP, then these NP complete problems aren't going to be in P. And so if you can show that any of them don't have a polynomial time algorithm, then also triumph in the other direction, where we know definitively that P is not NP. And sort of more practically, the reason people care about NP complete problems is that, again, since we don't really, most people think that P is not NP, that there are NP hard problems that are not, or NP problems that are not in P. If you can show whatever problem you're working on is NP complete, like pretty good evidence that you can kind of stop looking for a polynomial time algorithm for it. It sort of is a permission slip from theoretical computer scientists that you can kind of give up on your quest, because it's probably going to be intractable in this way. Okay, questions about NP completeness? All right, cool. So now that we have the definition of NP completeness, I'm going to give you an example of something of a problem that is NP complete. And it relies on something called conjunctive normal form. So if we have a Boolean logical formula, we say it's in conjunctive normal form. If we can write it kind of as this like big and, so the wedge, again, for those of you not up to date on your formal logic, the wedge is a big and the V's are ors. So effectively, if we can write our expression as some collection of ands of a bunch of or clauses. So maybe just helpful to give an example. This is something in conjunctive normal form. I have a bunch of Boolean variables. They're sort of put together in or clauses, and those or clauses are stuck together with ands. This is what it means to be in conjunctive normal form, and the bar on top just means not, and those are fine as well. And so now you can sort of see the decision problem coming, where if I have a Boolean logical formula in conjunctive normal form, I can ask, is there an assignment of the variables, of the Boolean variables, that makes the overall formula true? In this case, it's not hard to check that there is. You just, maybe you set x1 to be true and x1 to be true and x6 to be true. And then, this thing becomes true because x1 is true, this thing becomes true, this thing becomes true, and you add them all together, you get true. So in this case, there is a satisfying assignment. It's not particularly hard to find. But you can also come up with examples where it's much harder to find an example of a satisfying assignment. And in general, you can ask, given a thing in conjunctive normal form, is there a satisfying assignment? Because if I have something like x1 and not x1, then there's not going to be an assignment. And it turns out that this problem, the problem of looking at whether or not there is a satisfying assignment, is an NP-complete problem. And this is a bit of a corollary of the Cook-Levin theorem. Cook-Levin proves a slightly more general result about logical formulae. But this problem of looking at a CNF thing and determining if there's a satisfying assignment, I will call it the CNF sat problem. And it turns out to be NP-complete. The Cook-Levin theorem it's a beautiful result. It's something that I'm not going to show here because, as with most things, the first time you show something is NP-complete. And historically, this is the first problem that anyone proved was NP-complete. You have to give sort of an explicit, here's how you take an NP problem and give a reduction to SAT, right, or CNF SAT. And that takes a lot of technical details and a lot of work. That's probably a couple talks in and of itself. So I'm not going to go through the details, but a 30-second maybe gut intuition on why this should be true. Any decidable problem or anything that I can verify in polynomial time, I can then write a program that sort of checks it in polynomial time. That program is a circuit. That circuit can sort of be written, you can think of like hardware and software being the same thing. I can take that and just sort of write it as a bunch of ands, ors, and nots in its logical state. And then the certificate works if and only if there's a satisfying assignment. I know that's probably not super helpful, but maybe gives a little bit of intuition on why, like, it's not necessarily shocking that I can take any NP problem and turn it into a conjunctive normal form expression that has a satisfying assignment. Any questions about? Don't ask me to prove Cook-Levin, but about CNF or otherwise. Cool. So now we can finally sort of launch into the point of the talk, which is proving that the traveling salesman problem is NP-complete. And one thing I want to bring to your attention before we do that is just to say that these polynomial time reductions, they compose in sort of the way you would want them to. Namely that if I can reduce a problem A to B, and then I can reduce B to C, that gives me a reduction from A to C, because again, composition of polynomials is polynomial. This means that in order to prove something is NP-complete, it now suffices to show two things. It suffices to show that the problem is indeed an NP, that part's never going away. But now, if you remember, the other thing I'm supposed to show is that any NP problem can be reduced to the problem I care about. But if I have an NP-complete problem, that already gives me a reduction from any NP problem to that, which means I just need to show that that NP-complete problem reduces to the problem I care about. So I need to show that some NP-complete problem reduces to it, any one. Because again, any NP problem reduces to the NP-complete thing. And so if the NP-complete thing reduces to my problem, then every NP problem reduces to my problem, and we win. So this is how I'm going to show that the NP-complete problem, or the traveling salesman problem, is NP-complete. I'm going to show through a chain of these reductions that the TSP is NP-complete from using the fact that I have claimed without proof that CNF SAT is NP-complete. And so if I can show this chain, if I can show that CNF SAT reduces to some problem I'm going to call Cliques, which reduces to some problem I'm going to call Vertex cover, which reduces to some problem called Ham cycle, and that reduces to the traveling salesman problem, this is indeed enough to show that that the traveling salesman problem is NP-complete. Again, because we have already sort of demonstrated that it is an NP by taking the verifier to just, or the certificate to just be the list of edges that you're going to travel along, or something like this. Okay. Questions about why this why I can declare victory if I do this, or anything else that I have said before I spend the next 20, 25 minutes or so convincing you that TSP is NP complete and thus is worth caring about.
I feel like you're being very reductive, and I don't know if I appreciate that
I apologize.
with all your reductions.
Okay, so if we're all moderately happy with where we are, let's prove that traveling salesman problem is NP complete. So what I'm going to do is I'm going to not necessarily give the full proof of all of these things. I'm going to give the reduction, give the sort of the correlation between problems in the first and problems in the second. I'm going to show how you produce a new object given an example of the original object, and sort of describe the process by way of example as opposed to completely generally. So to prove CNFSAT is reducible to clique, what I need to do is take a logical formula in conjunctive normal form. And I need to produce for you an undirected graph and a natural number k, such that if there's a satisfying assignment to the Boolean formula, there's also that the graph has a clique of size k. And that's I suppose I probably should have explicitly said what the clique problem is, but you can see it there. It's given an undirected graph and a number. Is there a clique of that number? And a clique just means a collection of vertices where there's an edge between any two of the vertices in that set. So for example, to show, again, I'm just going to give you an example of the graph produced by a certain logical formula here. So for example, consider phi to be x1, and then wedge x1 or x2, wedge x1 or x1 bar or x2 bar or x2 bar. And this is a perfectly valid thing in conjunctive normal form. And now I need to produce for you a graph that has a clique if and only if this has a satisfying assignment. Not super hard to check that this does have a satisfying assignment. You set x1 to true and x2 to false. But here's how I could use a graph to do that. I'm going to make one node for each of these Boolean variables here, each of the literals. So here's my x1 node, here's x1, here's x2. Sort of because I know where I'm going, I'm drawing these in a certain order. And here are the nodes for the rest of them. And now the edges in this graph are going to be everything unless they're the two nodes I'm looking at come from the same clause. So for example, I'm not going to connect any of those three nodes because they all come from the same or clause here. And I'm also not going to connect anything that expressly contradicts itself. So I'm not going to connect, for example, x1 with x1 not. But every other edge that doesn't fall into one of those two camps is going to get connected. So I'm going to connect x1 to x1, x1 to x2. I'm not going to connect x1 to x1 bar, but I will connect it to x2 bar. Again, not going to connect these two because they've come from the same clause, but I will connect x1 to x2, and x1 to x2 or x2 bar, and then I think the last one is there. And so here's a graph, and I claim that this graph has a clique if and only if the original thing has a satisfying assignment. And in this case, here's one example of the clique. And if I find a clique, I'm just going to set all of those things to be true. So I'm going to set x1 to be true, x1 to be true, and x2 bar to be true, and in particular x2 to be false. This sort of relationship holds in both directions, because if I have a clique, that it has to give me a satisfying assignment, because I have because I have three variables that came from different clauses, and they're all true. And since there's an edge between all of them, none of them contradict each other. So there's no inherent self-contradictions there, and that's exactly what it means to be a satisfying assignment. And the logic holds in the other direction. If there's a satisfying assignment, there's going to be a clique because there's going to be an edge between them because they're not, they can't contradict each other, and they have to come from different from different clauses. So this process of taking something in CNF and producing a graph is this reduction that I'm looking for, where the graph has a clique of size the number of clauses, if and only if the thing has a satisfying assignment. And that's the reduction. So this now shows that clique or CNF set does indeed reduce to clique. Questions about the first argument? Okay, cool. They get more interesting from here. So now I'm going to take clique and reduce it to vertex cover. And vertex cover, the problem vertex cover is given an undirected graph and a natural number L. Is there a vertex cover of size L? And by vertex cover here, I mean a collection of vertices that touch all the edges in the graph. You can also think of this as a collection of vertices such that there isn't an edge between vertices not in the collection. So you can maybe see where this is going, where there's sort of some like complement property going on here. But that's what it means to be a vertex cover. And so I'm going to take an undirected graph and a natural number K and produce for you an undirected graph and a natural number L, such that the new graph has a vertex cover of size L, if and only if the old graph has a clique of size K. And so here we go. For this one, I'm going to take a graph on 6 vertices, and the vertices, the connections go like this. There are edges here, 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 there, and there. And we'll call this graph G. And so you can sort of see that there's going to be a 4 clique here between these 4 vertices. Those 4 form a clique. And the graph the new graph I'm going to produce, you can call G prime, is going to be the complement of this graph. The same vertices, but there's an edge between 2 vertices in the new one, exactly when there's not an edge between vertices in the old one. So that would look something like this, I think. We sort of produce the complement of the original graph. And now the claim is that the original graph has a clique of size K, of size, in this case, 4. So claim G has clique of size K if and only if G prime has a vertex cover of size the number of vertices minus K. And this is going to be our L. So in this case, the vertex cover is going to be of size 2. And again, not super hard to see that those 2 vertices form a vertex cover. Every edge in the new one is indeed hit by one of those 2 vertices. But the reason this works in general is, say suppose I have a clique of size 4 in the original graph, these 4. Let's look at the complement vertices that aren't in the clique. Those will form a vertex cover, and here's why. If there's an edge between, or ask the question, can there possibly be an edge between 2 vertices not in that vertex cover? For example, can that be an edge in the new graph? And the answer is no, because the complement, those 2 vertices aren't in the vertex cover, which means they were in the clique, which means that edge did exist in the original. And so that edge can't exist in the new one. And the logic applies in the other direction. If I have a vertex cover, take the other 4 vertices in the original, that must form a clique because there can't have been any edges between them in the new one because it's a vertex cover, which means all of the edges have to have been there in the original. So if there's any edge between two vertices here that were not in the vertex cover, then it wouldn't have been a vertex cover. And so, for example, this edge couldn't be in the new graph, so it has to be in the old graph. And so there is indeed a clique of size 4 in the old graph. And so this process, you can sort of see how this can generalize. This will work for any undirected graph. You produce its complement. Its complement will have a vertex cover of size v minus k, if and only if the original had a clique of size k. And that is the reduction from clique to vertex cover. Questions about this reduction? Okay, cool. Next one. I can leave it up. This is far and away kind of the ugliest of the ones. This gets a bit hairy, but we're gonna do it because we're going to actually do some legitimate reduction today, and this is the one. So the new problem is called Ham cycle, short for Hamiltonian cycle. And the question there is, given an undirected graph, is there a Hamiltonian cycle? And Hamiltonian cycle is a cycle, closed cycle, that hits all of the nodes in the graph exactly once. Similar to an Eulerian cycle, Eulerian circuit, but in this case, hitting all the nodes. And this is going to look silly, but the graph I'm going to produce the graph I'm going to reduce for you is this one here, which on 4 vertices, 5 edges, not a very exciting graph. But I'm going to show you how to take a graph like this and produce a Hamiltonian cycle or an undirected graph such that graph has a Hamiltonian circuit, if and only if the original has a vertex cover of size 2, or of any given size, but in this case specifically of size 2. Again, you can see those 2 vertices do indeed form a vertex cover. So the graph I produce should have a Hamiltonian cycle, but in general, it's exactly equivalent. So I've already drawn out all of the nodes we're going to need, but let me sort of explain to you where they come from. These 2 nodes come from the fact that I want a vertex cover of size 2. So I've been given this graph. I've asked, is there a vertex cover of size 2? I want a yes or no answer. So I'm going to draw 2 new vertices because I'm looking for 2 vertices. And then for every edge in the graph, I'm going to draw this, what I call an edge gadget of 12 nodes. And all of those are nodes. And now I'm going to draw for you the edges among these 62 nodes here. And the edges in this graph look like this. Each edge gadget gets this kind of structure, where sort of in big end, it looks like this. So you go across, and then those are connected. So each one looks like that. So we'll just quickly draw that in. So we're adding lots of edges to this graph. And then so that's how you sort of connect each one of those little gadgets. And now I'm going to, there's a very natural correlation between edges in the original and edge gadgets in the new graph. So I'm going to think of this edge here as sort of being that gadget as being corresponding to that edge in the original. And I'm going to label that so that we can remember sort of the UV edge. And I'm going to think of the top 6 nodes as somehow corresponding to U and the bottom 6 is somehow corresponding to V. Similarly for U and W, This one will be the middle one for V and W. This one will be the right one for V and X. And this one will be the bottom one for W and X. Okay. And now that we're thinking of it like this, I'm going to connect for each vertex in the original, for each of U, V, W, and X. I'm going to connect all of the edge gadgets that correspond to one of those nodes or to one of those vertices. So I'm going to connect the U to U. And since there's only two vertices or two edges coming out of U here, that's all I do. For V, I'm going to connect V and V with V. So you look at all the V's. Similarly, if we look at all the W's, we connect the two W's together. Sorry, there's a third one. So we connect the W to W, and then we'll connect X with X.
And it doesn't matter like which endpoint you pick during this process.
Nope. You can, yeah, these are very like commutative. You can choose any of them to start and end with. They will all work in exactly the same way. So those are more edges. And now I'm not going to draw them because the diagram gets very messy very quickly. But all of the edges, all of sort of the ends of these gadgets that are not connected already, that are sort of the end point of these vertex chains, if you will, they will all both connect to this node and to that node. And this one will connect to there and there, and this one will connect to there and there, and etc. I know. This is a big mess. It's a disaster of a graph, but it's really cool. And here's why. Let's look at any individual edge gadget. And maybe to be explicit, maybe this is the UV edge gadget down here. There's only, if we have a Hamiltonian cycle in this graph, and we think about what happens to this particular edge gadget, you can sort of convince yourself that there's only three possible ways that the Hamiltonian cycle could traverse this gadget. It either comes in, it either comes in this way and goes out this way, or it comes in this way, sort of comes down here and then comes up and goes out, or it goes the other direction from the bottom, comes in, goes across that way and goes out. Those are the only three ways that this could happen. And in particular, it can't do something like, I don't know, come in here, go down, go across, and then up, and then out, or whatever. Because if I do that, how do I get to, for example, this node? You're not going to be able to, right? So those three options are the only possible ways for a Hamiltonian cycle to traverse each one of these edge gadgets. And that is going to correspond exactly to whether U is in the vertex cover, V is in the vertex cover, or both U and V are in the vertex cover. Those three different ways correspond to exactly those three possibilities. And I also want you to notice that for all of those, if I enter the edge gadget on the V side, I have to leave on the V side. Something to keep in mind for a second. So now, given all of that, I'm going to take the vertex cover V and W and show you how to produce the Hamiltonian cycle on this graph. And the way we do it is by starting at one of these nodes, and then we're going to travel to the other node via the V chain. So along the V path. And remember, this point here is connected to this to that node. I didn't draw them all because I didn't want to get bogged down, but there is this connection. So I'm going to take that connection. Now I'm going to traverse this edge gadget in this way, because V is in the vertex cover and U is not. So I need to cover all the U's. I'm going to keep going. V and W are both in the edge gadget. So I'm going to shoot straight across on V. I'm going to keep going. They get to here and go across this one in this way because V is in, X is not. And then I've reached the end. So I go to this node. Now I'm going to come back via the other one, the W chain. So again, let's get to the W part. W is in the cover, X is not. So I go like this. I come up here. W is in and V is in. So I'm going to shoot straight across. Over to here. W is in, U is not. So I need to go like this. And then I get to the end and I can come back to the beginning. And this was a Hamiltonian path. All right, so I have taken an edge, a vertex cover, and produced for you a Hamiltonian path. The reverse process is sort of exactly the same. The reverse process is exactly the same. If I have a Hamiltonian path, each edge gadget looks like one of those three options. And so I choose either just the one, just the other, or both of the corresponding vertices to be in the vertex cover. And critically, go back to that comment I made about if I come in on the V side, I leave on the V side. The reason I chose exactly two of these nodes to include is that to get from one to the other, I travel along exactly one vertex chain between them. So if I'm looking for two vertices in the cover, I use two of these nodes because going there will take me on one path and back will take me on another. And since I've hit all of the nodes, I've hit all the edge gadgets, that those two vertices have to touch every edge in here because I've hit all the edge gadgets in this graph.
Just letting you know, this video is going to have a banging thumbnail. This boy right here.
Yeah, that's a good choice.
So just to clarify, Nick, so this, regardless of the size of the vertex cover, this same exact edge gadget, like this is the same construction, you just change the number of like extra vertices, right? Like,
sorry, say that again.
You don't need a new edge gadget for like each K. Like you don't have to do like some like 3-track thing. It's just this thing every time. It's just the number.
These things stay the same regardless of the complication of the graph. The number of these vertices changes with how many vertices you're allowing yourself for the vertex cover. And obviously the number of edges is then going to explode with that because each of these sort of endpoints, if you will, are connected to not just two of them, all of these vertices. You sort of give yourself as many options as you can for traveling from one vertex, from one of these to another one via any of the vertex chains you would like. And this goes back to that question you asked earlier of like, does it matter which way you do it? And the answer is no. And for exactly that reason, that I want to be able to, I could have traveled from here to here along W and then back along V, or, from here to here along, like there are lots of options here. And also interestingly, this will have exactly sort of, there's a one-to-one correspondence, not just between if there's a vertex cover, then if there's a vertex cover, but between the vertex cover and the Hamiltonian cycle. So if there are two possible options for vertex covers, there will be sort of the corresponding Hamiltonian paths in this graph.
Hamiltonian cycle, just for reference.
Hamiltonian cycle, yes. Yes, thank you. Okay, I know that's a lot, but this kind of sort of ish makes some sense. Okay, awesome. If we're happy with this, then we're going to be very happy in a second because the last reduction is very easy. And this one, just because I don't need to get more complicated than I need to, I'm going to take a graph. So this is reducing from Ham cycle to the traveling salesman problem. So I'm going to take a graph and I'm going to construct the new graph. The weighted graph is going to be the complete graph on those vertices. And the weight is either 1 if that corresponding edge was in the original graph, and n plus 1 if it was not in the original graph. And now the question, is there a complete Hamiltonian cycle with weight no more than 4 in this graph? Well, that happens exactly when there's a complete Hamiltonian cycle in this one, because each of the Hamiltonian cycle paths will contribute a weight of 1. And since all the other ones have weight already bigger than the target weight, you can't take any of them. So this is sort of a very quick reduction of Ham cycle to the traveling salesman problem. Questions about that? Fairly straightforward. Okay, so that's it. That's the proof. We've shown the thing we want to show. We've shown that you can reduce from CNFSAT to traveling salesman via this sort of ridiculous chain. And since CNFSAT was indeed NP-complete, this means that any NP problem A, can be reduced to CNFSAT and thus reduced to the traveling salesman problem. And so TSP is at least as hard as every other NP solvable problem. And so it's NP-complete. Again, it's in NP because it can be polynomial time verified. Just here's the order of the edges that you travel along. And since it's in NP and everything can be reduced to it, it is NP-complete. And that's the proof. That's why we're allowed to care about the traveling salesman problem, because it's the hardest NP problem for some definition of hardest.
All right, let us thank the speaker.
Yes, correct, Sam. No, we can't care about graph isomorphism anymore. This is it.
Starting off strong this year. Any questions for the speaker?
Yeah, Nick. So we proved like implicitly that all of these things are like NP-complete problems, right?
Yes.
Is there like a big list, possibly famous, of NP-complete problems?
I wish you didn't mention this because I was going to mention this myself, but
Okay.
yeah, famously, very early on in the sort of the study of this, a guy named, I think his first name is Richard, but Richard Karp wrote, didn't prove, but claimed very assertively that he sort of gave 21 problems and gave a little a tree diagram for how to use reductions from one to another to show that all of them are NP-complete. So if you're curious, there are a whole bunch of these like this. I could have chosen a number of different problems to sort of claim as the granddaddy of all NP problems. But I have a particular affinity for the traveling salesman problem, and that's why I went with this. Also, interestingly, this isn't quite how Karp would have done the traveling salesman. He does it in a slightly different way, but I think this is like at least easier to visualize, sort of in a 30-minute presentation. So, yeah.
I'll have to check out those 21 problems of Karp's.
I had a question. It seems like so we know for these NP-complete problems that there is a reduction in both directions. And it seems like for all of the ones we looked at today, it was sort of the same trick in both directions. Are there any examples where like one is much harder than the other or something like this?
So let's be careful. And this is a really good question, because this is a thing that you have to sort of get used to. You have to get used to what do we mean by the if and only if versus the reduction. And in particular, when we're looking at this, I've given a reduction from vertex cover to Ham cycle. I've taken this graph and produced for you this one. It's really, really hard to take just an arbitrary graph that has a Hamiltonian cycle, maybe not, and produce a graph that has a vertex cover, maybe not, right? That's not the binary or the mutual direction thing. The mutual direction thing is only this has a Hamiltonian cycle if and only if this has a vertex cover of size 2. But the reduction, given just any undirected graph with maybe a Hamiltonian cycle, maybe not, producing a different graph and a number such that that graph has a vertex cover if and only if the original has a Hamiltonian cycle, that's not sort of demonstrably not what I did here. The both directions thing you're thinking about is because I know I can reduce this, like now that these are both NP hard or NP complete, there's got to be a reduction from both of them, right? This sort of trivially now I can go from vertex cover to Ham cycle to 3 sat to vertex cover, or to CNF sat to vertex cover. Like that's probably going to be the way I would sort of argue this, is like, once you have an NP complete problem, if you get a reduction in one direction, you can then go back to the original NP complete problem to get back to where you sort of want to be. But these are not necessarily like these functions, these reduction functions from inputs to A to inputs to B. Those are not like the inverse of that function isn't necessarily well defined. Maybe a good way to say that. Does that answer that?
Yeah, maybe one more follow-up. So
Yeah.
mathematically speaking, obviously you can just use transitivity and none of us would really bat an eye. But I also know that like, as far as CS people go, they often do care about like trying to find a more direct route to something, especially for efficiency reasons. So I was wondering if there are any like interesting examples where like we don't know some like direct argument for why one is reducible to the other. We only know the transitive one or something like this.
I'm sure they exist. My experience with this has all been sort of through coursework where like, here's a thing, produce a reduction to this other thing. So most of my examples are positive examples. Yeah, I'm sure you can sort of come up with like, just pick 2 arbitrary NP complete problems and say, I want a nice reduction between the 2 of them. It's going to be tricky. Even this, like taking CNF sat and producing traveling salesmen, like you sort of need to go through all of these reductions to get there.
In particular, this one seems like a little bit of a bottleneck, patience wise.
Yeah. So it is a bit like you're often going to go through these chains of reductions, at least as far as I am aware. I'm not a leading expert in this kind of thing. I've taken a class on it, but this is the sense I get.
Amazing. Any other questions?
Yeah. Shoot, what was my question? Oh yeah. What does it mean to be NP hard? I've heard this word said.
Yep. NP hard means you're at least as hard as every NP problem. So, let me, where do I want to put this? I can draw this down here. So if you're, you can't really think about this in this way, but sometimes it's helpful to draw this graph of like, difficulty of the problem. So, over here being less difficult, less hard, and this being more hard. NP problems are sort of like on this side of the thing. P problems we think are like sort of here. So this is, this would be P, this would be NP. Anything harder than the hardest NP problem, we say is NP hard. So those would be NP hard. And NP complete is exactly this point here, where it's harder than, or it's at least as hard as everything in NP and still in NP. So the other way you can define, sorry, say again, Baki?
It's the infimum of NP hard.
Yes, it's it is the attained infimum of NP
Very
hard.
good.
And that's actually another way that you can define NP completeness, to first define what NP hard means, and then say, something is NP complete if it's in NP and NP hard.
Yeah, and I think like just an equivalent way of saying that is like we had this like two things needed to be an NP complete, and NP hard is just you're not necessarily in NP. Like you don't care about that. You just have the polynomial reduction.
Yeah, that's
Nice.
that's a good. Yeah. And there are lots of problems in this NP hard category. There are lots of things that are not even close to NP solvable. So there, let alone P equals NP. P, if we can show that P equals NP, it's not like every problem we can think of is easy. It's just showing that if we can verify it quickly, that we can also find it quickly. That's what the P versus NP question is asking.
All right. Any more questions?
Yeah, can you go back a slide for 1 second?
Yep. Here.
One more. Sorry. Okay. Why did you need to make a complete graph? Couldn't you have just done the original graph and put 1 for all the edge weights?
I think in traveling salesman, like just like formally you put all the weights in. I mean, you can add like weight infinity to the edges you don't want to take basically, or that aren't there. And like it basically does the same.
Yeah.
I'm just saying like for this function, couldn't you have just, instead of creating the complete graph on the server?
So I think what Sam, so what Sam's getting at is something that I didn't really touch on, but traveling salesman is generally phrased as given a complete graph with weight.
Okay.
Is there a path of small weight? Right.
Gotcha.
There's certainly a path of there's certainly a Hamiltonian cycle if it's complete. You're sort of looking for the smallest one. And that's why in general you complete these things. I guess I could have said that, but didn't. But yeah, that's sort of in standard practice. That's sort of what the traveling salesman problem is actually asking.
Gotcha.
Fantastic. Any more questions? Wonderful. Let us thank the speaker once more. Great job, Nick. Sam, who do we have next week?
Jason.
All right.
He's had this slot saved for like over a year, I think.
I have been
Close to it.
anticipating this much. Very nice.